Hey everybody, how's it going? Welcome to our next lecture. This is Unit 9, Circulation Patterns of the Atmosphere, where we will explore how the air, we learn the atmosphere, right? The purpose, one of the main purposes of circulation is to kind of redistribute heat, to make life kind of habitable on various latitudes on Earth, right? And so we're going to explore that a little bit more here with this idea of circulation patterns and kind of get into exactly how the air um, in the atmosphere circulates throughout the earth. So let's begin and talk about winds and how they flow. And, um, winds very rarely flow in straight lines. Rarely, okay? When they do, more so, or at least if they kind of follow the patterns of latitude, we call that zonal flow. So I guess you could say more kind of horizontal winds, excuse me, horizontal winds compared to like parallel with latitude. Um, and on the other side, winds that flow more parallel to longitude, we call those meridian flow. Okay, so meridian, that makes sense. Like meridians, longitude. And then zonal for, you could think of zonal as parallel. We know parallels are latitude. But again, this is kind of a general overarching saying if winds, and they never, like I said, they hardly ever flow in straight lines. Like a zonal flow would be something kind of like this, like a wave, or meridian flow, something like this, vertical. That's kind of the gist of it. Okay. Now, speaking of specifically, the real driver here, and you're going to hear me reference this numerous times throughout the rest of the semester, because this really is a huge component of atmospheric circulation. So the concept that heating, year-round heating, okay, like it's always pretty much the same type of heating along the equatorial regions of the Earth. Okay, so where the equator is, this produces what's called a thermal low pressure belt. Um, and in this thermal low pressure belt, the air rises, okay, because we know that warmer air is lighter and it ascends, okay. And so the air rises in this zone, and we call this the Intertropical Convergent Zone, or ITCZ. ITCZ, that's going to be something that comes up frequently throughout this course, okay. So let's do this. I have a whiteboard here on the computer, and I'm going to do a little snapshot of our notes like this. And then I want to bring over the whiteboard so that you can see what I'm talking about a little bit better detail. Don't really pay attention to this side. This is kind of for me reading my notes as I'm going along here. Um, what I wanted to bring up was this whiteboard here. Okay. And I've got a couple illustrations here to try to explain myself. And what I'm talking about with this ITCZ. Okay, so as we said in that statement there, year-round heating near the equator. Okay, so here's our sun. Okay, here's our sun, and we know the Earth is on a tilt. That's okay. Doesn't really matter in this case because we're getting consistent vertical sun in this region. And so if this is our equator, think about it like this: between the Tropic of Cancer, okay, which is at in the northern hemisphere at 22 and a half degrees north, and the Tropic of Capricorn, which is again 22 and a half degrees now south, okay. So these two tropics, okay. Think of all of how these words are kind of synchronous to each other, right? So we have the intertropical convergent zone. What we're talking about is inter meaning the two tropical latitudes, intertropical convergence zone. So zone being here, this being the ITCZ, this zone between the two tropics, intertropical. And convergence meaning that the air is going to converge from the northern hemisphere and the southern hemisphere. And they're converging, meaning that the air is going in this direction towards the equator and this direction. So north in the southern hemisphere and south in the northern hemisphere, right? Reason being, again, is because of this immense amount of heating and solar radiation that is incoming to this zone. So in both the northern and southern hemispheres of the tropics, you have intense low pressure events, intense heating, which causes intense low pressure events. And what do we know about low pressure? Low pressure and heating, it makes the air go up. And so naturally where the air actually converges and meets each other is right near the equator. And that's where the air actually kind of goes up like this. Think of the equator as kind of like this invisible wall in a sense. And maybe this helps, and the air is coming towards it and it kind of goes up like this, okay? And so this ITCZ causes the air to diverge poleward in the northern and southern hemispheres. So let's do this. Okay. Okay. So now it's a new graphic, but now we're looking at the Earth from different perspectives, okay? Actually, here, let's zoom in like this, okay? On this side. So here's our equator, and we have that warm air traveling towards the equator in the northern hemisphere, warm air traveling towards the equator in the southern hemisphere, and then this is where they converge right here. Okay, this would be where they converge. And so what we're saying is now that as the air converges, it's going to rise, and then it's eventually what it's going to do is it's going to return kind of back where it started, but at a much higher altitude. And so we know as air rises, it cools, okay? And to a certain point, once it gets cool enough, it actually starts to descend. And so this whole sequence is as the air in both hemispheres, okay? As the air rises and actually moves, then it diverges. So it first converges at the poles and then goes up and then diverges away from the poles. And as it is diverging, it's cooling. Okay, and so as it's cooling, then it eventually is going to descend, and it descends around 30 degrees latitude in both north and south. Okay, so we call this descending air. That would be here, right? That's why I made these blue. So this air is cooler now, and it drops. Same effect with this. And this air that drops here, we call these the I put ST highs, subtropical highs. Okay, they're not quite the tropics anymore because we are now beyond the tropical latitudes. So it would be the subtropics. And we know as air descends, it creates high pressure. Therefore, we have subtropical highs in both the northern and southern hemisphere. Okay. Now, other notes here. Okay. Thanks to our friendly Coriolis effect, there's more to it. So again, since we mentioned, rare that the air just kind of follows this north-south pattern. I mean, sure, there's a meridian flow, but let's think beyond that and take into account the Coriolis effect for this next discussion. Let's see. As the air returns to the equator, okay? So again, this is like a cycle, right? This is like a cycle. As the air returns to the equator, so now we're looking at the Earth kind of from straight on position. As the air returns to the equator like this, what ends up happening in the north, it is deflected to the east. So it's like the winds flow from west to east. Maybe my finger's not helping because I think I'm sure you're looking at the opposite way. Look at the graphic, that's what's important, okay? So in the north, we go from west to east, and the rotation is counterclockwise, okay? Counterclockwise. Counterclockwise. Whereas in the south, it would be, in the south, it would be, no, what am I saying? Counterclockwise. Anyways, they're both counterclockwise. Okay, duh, I'm looking at these. But the difference is that as you look at the south, where the equator is located, okay, you notice that in the southern hemisphere, the winds are actually flowing from east to west, okay, east to west. Technically, these are both counterclockwise circles because it's low pressure. But yeah, east to west in the southern and west to east. Well, we call these northern hemisphere winds, we call these the northeast trade winds, okay? And then in the south, we call these the southeast trades, okay? Southeast trade winds, okay? Um, Now, there's a little bit more to it because the air just doesn't stop at 30 degrees latitude. The air actually, air actually continues to circulate, and then things start to shift a little bit differently, okay? So, whoops. Once we get to that 30 degrees, latitude, what ends up happening is the air beyond 30 degrees, kind of the same type of cycle happens, and where air then continues poleward. And in this instance, though, the air actually circulates clockwise. Okay, clockwise. Remember, this is high pressure near 30 degrees. Okay, because of the subtropical high, and so the air that is kind of generated in this region um, creates this high pressure, and then the Coriolis effect actually deflects. I'm only looking at the northern hemisphere here, so the Coriolis effect actually deflects the air to the right in this instance. Now, as we look at the southern hemisphere, it would be the opposite. Okay, just so you know. But yeah, now we're looking at air being deflected to the right in the between 30 and where the air stops. The circulation kind of pattern stops is at 60 degrees north latitude. And so it's actually quite easy to remember. We have 30, 30, 30, right? So from 0 to 30, 30 to 60, 60 to 90. That's kind of how this works. And so between the 30 and 60 range, we call that the westerlies, okay? Because the air is flowing from west to east, okay? West to east, westerlies. Yeah, and then at 60, what ends up happening is the large cells of high pressure formed at the poles. These are called polar highs, okay? And so the large cells of high pressure, the air moving from the polar highs to the equator is sharply deflected and called easterlies. Yeah, called easterlies. Let's see. The polar easterlies meet the westerlies. So essentially what we have here, easterlies in the from 60 to the North Pole. You basically consider this the poles. The air is flowing more easterly. And so the easterlies and the westerlies meet, and we just kind of have this never-ending cycle of air circulation and flow, okay? And so that's really what I wanted to kind of get across to you guys. And if we look at the notes, we've gone through a lot of it so far. This is not a very long section, but we've just covered everything related to the ITCZ, okay? ITCZ. Now, let's take a look at the something else that happens here. Because the ITCZ actually tends to shift a little bit. So maximum solar heating shifts throughout the year because of seasons, and it causes seasonal north and southern movements of these pressure, wind belts. Okay, those were belts of wind. We can think of them, and this results in individual pressure cells. So let me show you what I'm talking about here in the slide number 9. This is the kind of shifting position of the ITCZ. So here we go. ITCZ in July. This would be the like the very center of it. Okay, it's not always necessarily the equator. Okay, and so the ITCZ in July, which we know is the summer of the northern hemisphere. And so if our equator is in the middle, notice that in the ocean, actually in both July and January, the ITCZ is pretty consistent, right? And so think about why that might be. Well, water doesn't really heat up at the same rate that land does. And so therefore you kind of have this constant heating no matter what time of year it is. So that's why over the Pacific Ocean, there's not a ton of change. But when we get over to places like the Eastern Hemisphere, you know, where you have Africa, Asia, and Europe, the majority of the land mass is in the Northern Hemisphere. It really is. And so you have this kind of shifting of the ITCZ, whoops, like this, where it shifts a little bit northward here. Okay. And it actually at some points rises, over 25 degrees north. And so what that does is it actually shifts the entire, cycle of those wind cells I was mentioning earlier. So something from, instead of at the 30-degree mark, say it shifts up to, 35 or 40 degrees. I don't know what the exact numbers are. But I'm just trying to make a point to you guys that based on seasons and where the kind of average ITCZ is at that moment in time, that's where your kind of your subtropical highs actually will shift a little bit. Or I guess I should say the entire ITCZ itself will shift a little bit, which causes an entire shift of everything else, okay, in terms of circulation. In the south, we have a little bit of the same thing happening because of this large landmass in Africa and some of the influence of South America, but not as strong of an influence as we see here. The furthest southern in January is about 20 degrees. So that means, let's put it this way. As I'm looking at this, I would say you have more tropical weather in these parts of, in the Africa and Asia, Southern Asia type of, places, as opposed to like Southern Mexico and or Central America. I mean, there's similar climates, but yeah, because of this, where the ITCZ, ends up being during various seasons throughout the year. Okay, so next we have three, these things, I'm calling them these wind belts, right? Well, they actually have names, right? So you kind of got the gist of how they're detailed, but they actually have names. And there's three cells. I want you to remember cells. If I ask you about cells in this lecture, I'm referring to one of these three things, okay? The Hadley cell, the polar cell, or the Ferrel cell, okay? So you already know kind of the flow and the direction of winds and what's going on and why and the pressure that's going on there. I'm gonna pull away now and I'm gonna show you guys some YouTube example, and that's actually gonna be it. So we're gonna watch this video, which is kind of a refresher about the ITCZ, and then we'll talk about, and then it will move on and talk about these cells. So I want you to know and recognize these cells and how they work, okay? So that's gonna be it for me. I'm going to turn my screen off, and we'll see you next time. Thanks.
Why are all the Earth's deserts on a similar latitude? And what gives different parts of the world their climates? What gives us jet streams? And why do we get prevailing winds? It's all to do with the global atmospheric circulation caused by the Earth's rotation. We'll look at what this is over a series of short explainer videos. The first step to explain how global circulation patterns affect weather and climate is to understand how temperature varies across the globe. Global circulation is caused by different parts of the world heating up differently. In this first video, we will look at what causes this differential heating. The sun is our main source of heat. This heat travels to us through space in the form of radiation. This radiation is absorbed by clouds, atmospheric gases, and by the Earth's surface. Some parts of the Earth receive more of this radiation than others. The main reason for this is the curvature of the Earth. This curvature means that at higher latitudes, the radiation from the sun is spread over a much larger surface area, while the same amount of energy is much more concentrated near the equator. The radiation also travels through a greater depth of atmosphere nearer the poles in comparison to the equator, so more radiation is lost to scattering and absorption by gases and particles in the atmosphere. The tilt of the Earth also means that polar regions do not see daylight during the winter. Here the Earth is continuously sending out heat to space without any compensating incoming heat from the sun. These cold polar regions are where we see lots of snow and ice. Snow and ice, and also thick cloud, reflect a lot of the sun's radiation back into space. The reflectivity, or albedo, of the underlying surface is an important factor in determining how much of the sun's radiation is used for heating the Earth. The combined effect of all of these processes sets up a thermal gradient between the equator and the poles. In fact, the global radiation balance is such that poleward to 40 degrees latitude, the outgoing heat radiation from the Earth exceeds the incoming heat radiation from the sun. Global circulation acts as a clever air conditioning system, redistributing the heat, stopping the equator becoming hotter and hotter and the poles becoming colder and colder, and these locations becoming uninhabitable. This circulation takes the form of 3 large atmospheric cells, which exist in both northern and southern hemispheres. Our next video shows these cells in more detail. Why are all the Earth's deserts The last video showed that different parts of the Earth heat up differently, with the equator receiving more radiative heat from the sun than the poles. And the purpose of global circulation is to redistribute this heat. If the Earth did not rotate and was a simple landmass with no oceans, we would have a single circulatory cell in each hemisphere, where hotter air would rise at the equator and flow toward the poles. The air would sink as it cools and then return towards the equator. But the unequal distribution of land and ocean and the speed of the Earth's rotation make this circulation system more complicated, giving us a 3-cell pattern which exists in both the northern and southern hemispheres. The largest cells are the Hadley cells. At the equator, the warmer, less dense air rises. It rises to a height of about 18 kilometers and spreads out underneath the tropopause. The tropopause acts as a lid to the lowest part of our atmosphere, which contains all of our weather. The warm air spreads out towards the poles, gradually cooling and sinking as it moves, before descending to the surface and flowing back to the equator. The smallest cells are the polar cells. Cold, dense air descending in the polar regions flows at low levels to about 60 to 70 degrees north or south. As the air leaves the polar regions, it starts to warm and rise, returning to the poles at high levels. Between the Hadley and polar cells are the Ferrel cells. Unlike the other cells, the Ferrel cells are not driven by temperature. These cells flow in the opposite direction to the Hadley and polar cells, acting like a gear. These circulating cells not only transport heat from the equator to the poles, but also result in semi-permanent areas of high and low pressure. due to the rising and descending parts of the circulation cells, giving us our climatic zones. Where air is rising, an area of low pressure is created, so these areas see much more rainfall. This is why the largest areas of rainforest are found near the equator, and why the United Kingdom has a relatively wet climate. Where air is descending, an area of high pressure forms, giving largely clear skies and little rainfall, which leads to the desert regions. But not all deserts are hot. Antarctica sits under the descending branch of the polar cell and is also classed as a desert. With more precipitation falling in the Sahara, Antarctica is the largest and driest desert overall. Check out our video on atmospheric pressure for more on how pressure leads to weather. Our next video shows how the rotation of the Earth gives us jet streams and prevailing winds.